might be interesting to read. So we'll do it and see how we go. Let me just put this straight. It's gone a bit skewiff. There we go. So, I think it's going to give us more details about the GSM and CDMA, which would be very interesting. All consumer cell phone devices function through the transmission of radio waves on a cellular network. The cellular network itself is composed of a collection of individual cells that include a fixed location transceiver, a device that transmits and receives radio signals, also referred to as a cell tower. The collection of adjacent smaller cells in the cellular network enables cell phones and towers to use low-power transmitters, thereby allowing for the same frequencies to be reused in non-adjacent cells without interference. Together, the individual cells comprise the cellular network that provides coverage over a large geographical area. In the United States, two major nationwide cellular technologies in use are CDMA, Code Division Multiple Access, and GSM, Global System for Mobile Communications. While technologies are rapidly evolving to meet consumers' increased demand for better coverage, increased call quality, faster data and transfer rates, and increased accessibility in the context of this report, the terms CDMA and GSM group together multiple, sometimes successive technologies that are implemented by the service providers that maintain the service networks. In the United States, Sprint and Verizon networks use CDMA, AT&T and T-Mobile use GSM. For both the GSM and CDMA technologies, transmissions occur at specific radio frequencies, which are allocated and regulated by the Federal Communications Commission. While the transmission of radio signals frequencies can occur at the same frequencies for both technologies, they differ in the method by which information is incorporated and transmitted within frequency bands. In telecommunications, these are referred to as signal modulations. Because this process differs for CDMA and GSM, cell phones are not interchangeable between the two network technologies and will only function on one or the other. The constantly evolving cellular technologies are commonly referred to by their successive generations. G. The first generation 1G devices were analog phones as opposed to the digital phones of today. Digital voice systems of the second generation, 2G, replaced the analog system of 1G. At that time that these studies were being designed, 2G technology was the primary technology in use, and 3G technologies were emerging. Therefore, the current studies were conducted using modulated signals that replicated the 2G and 3G technology in use at the time. Over the course of the studies, however, more advanced 4G technologies were developed. Currently, all of these technologies, 2G, 3G and 4G, are still actively in use for mobile communication applications. 2G and 3G are still the basis for voice calling applications, while 3G and 4G technologies were primarily developed to offer faster access to the internet. Some of the 3G technology is based on 2G technology. While 2G technology is being phased out in the United States, this technology will remain in use in other places throughout the world. More advanced and efficient technologies that are currently in development and not yet deployed, termed 5G, will utilize higher frequencies than existing technologies. So that's actually very good. I'm going to highlight that as well. So, radio frequency radiation, measurements and applications. RFR is a form of non-ionizing electromagnetic energy that consist of propagating electromagnetic waves of oscillating electric E and magnetic H fields that move together at the speed of light. RF waves are characterized by their wavelength, the distance covered by one complete cycle of the electromagnetic wave, and their frequency, the number of electromagnetic waves passing a given point in 1 second. The frequency of an RF signal is expressed in terms of hertz, where 1 hertz is equivalent to 1 cycle per second. RF radiation refers to the region of the electromagnetic spectrum from 3 kHz to 300 GHz, as opposed to ionizing radiation, which contains enough energy when passing through matter to break chemical bonds or remove an electron from an atom or molecule to produce charged ions. Non-ionizing radiation has at most sufficient energy for excitation of an electron to a higher energy state. The intensity of an RF field can be expressed by its electric and magnetic components, and is measured in volts per meter for electric fields and amperes per meter for magnetic fields. Another measure of RFR is the power density, which is defined as the power per unit area and is expressed in watts per square meter. The quantity used to describe the amount of RFR energy absorbed by the body is referred to as the specific absorption rate, abbreviated SAR, which is expressed in watts per kilogram. SAR is a function of the geometry and the dielectric loss properties of biological tissues absorbing the energy, which results from the interaction of electromagnetic radiation with constituents at the cellular and molecular level. The square of the strength of the induced E field and the mass density of the exposed tissue. The SAR value is derived by averaging the absorbed energy over a specific volume, typically 1 gram, 10 grams, or the whole body, for regulatory purposes. Different applications utilize different frequency bands within the RF portion of the electromagnetic spectrum. RF frequencies for radio and television are in the 145 kHz to 850 MHz range. Wireless communications and networking typically utilize frequencies between 800 MHz and 6 GHz. Cell phone networks that are currently in use, 2G, 3G and 4G, utilize frequencies in the range of 600 MHz to 5.7 GHz. In the United States, wireless telecommunications networks and devices operate in bands at frequencies of nominally 800, 850, or 1900 MHz for 2G, 850, 1700, or 1900 MHz, or 2100 for 3G. 600, 700, 800, 850, 1700, 1900, 2100, 2300, 2500, 5200, or 5700 MHz for 4G. So, as you increase the Gs, all the other Gs are incorporated. The next generation, i.e. the 5th generation of wireless technology, will also utilize the RFR spectrum above 6 GHz. Other terms are also used in the literature for part of the RFR spectrum. For example, microwaves for frequencies above 1 GHz, millimeters waves for frequencies above 30 GHz. And here's a lovely figure here. You've got the energy in electron volts, and you've got the frequency in hertz. Power lines, radio and television. Cellular, it's got an arrow pointing exactly where that is. So you've got cell towers, radio and television, and microwaves. Infrared, getting into visible light, ultraviolet, and then you're creeping into the ionizing stuff, which is X-rays and gamma rays. So all of that's really good as well. It's kind of consolidated technical information. which is great to have because then you know exactly what you're talking about. Cell phones and RFR. Cell phones and other commonly used wireless communication devices are essentially two-way radios that contain both a receiver and a transmitter. When a user makes a call, voice sound is converted into digital information. The information is imposed onto RFR and transmitted to the nearest base station, commonly referred to as a cell tower. So I find that incredible how that happens. That receives and transmits RF signals and forms a bridge to the rest of the communications infrastructure. The base station receives and transmits radio signals in its area or cell. As the user moves around, the radio signal can be relayed within the communications network from one cell of coverage to another, maintaining call connection. The call is routed through the communications network either through a landline phone or another wireless phone, again using radio signals. To conserve energy and minimize interference, mobile phones automatically regulate the RFR signal strength and hence the emitted field to the lowest power level possible for a connection to be made. However, in a poor transmission environment caused by either a distant base station, presence of obstacles between the base station and the mobile phone, or interference from adjacent cells, there is a higher output power and emission from the mobile phone in order to make a connection. Therefore, the better the connection, the lower the power output of the wireless device. That's why you shouldn't use your phone in a lift, for example, or deep underground, because it's going to be trying really hard to locate the tower. Or if you're out in the sticks on the hill and you've got low signal, just turn it off. It's much better. Cell phone RFR signal modulation. In wireless telecommunications, modulation is the process of conveying digital or analog signals or information, the message, by varying one or more parameters of another signal, the carrier, typically at a much higher frequency. The modulated carrier contains complete information about the message signal, and the original message can be recovered by a suitable signal processing of the signal when received at a remote location, base station. One of the main goals of the modulation used in mass wireless communication systems is to transfer as much data as possible in the least amount of spectrum. Over the years, multiple modulation techniques have emerged to achieve and improve spectral efficiency, either when considering a single user in isolation or multiple users simultaneously using the same spectrum. The first generation 1G of wireless technology, introduced in the 1980s, used analog frequency modulation for voice calls. This technology was replaced by second generation 2G networks that were digital, provided encryption, was significantly more efficient, and introduced data services, i.e. text messages, picture messages, and multimedia message service, MMS, in addition to voice calls. The 2G networks became commercially available in 1992 and used three common multiple access technologies for accommodating multiple simultaneous users. Frequency division multiple access, FDMA. The available spectrum is split into a number of distinct parts, channels, each large enough to accommodate a single user or call without overlap. All users utilize their channel 100% of the time for the duration of the call or message. The channels are normally of equal bandwidth. Time division multiple access, TDMA. I've always wondered what these mean. The available spectrum is allocated to a single channel, each user or call assigned a certain portion of time. Code Division Multiple Access, CDMA. The available spectrum is allocated to a single channel. Each user or call is assigned a unique sequence code to spread the message over the available spectrum. All users use the whole of the spectrum all of the time. At the receiver, the same unique sequence code is used to recover the desired signal from the sum of all the user calls. That's pretty fascinating. 2G systems used a combination of FDMA and TDMA for GSM or various versions of CDMA. For example, CDMA1 IS95. While the 2G technology continues to operate, subsequent third and fourth generations of network technologies were introduced in 1998, 3G, 2006, 4G, and 2011, 4G long-term evolution. So that's what LTE stands for, long-term evolution. These technologies were developed to support increased data demands for multimedia access with increased bandwidth and transfer rates to accommodate internet-based broadband applications, including video conferencing, streaming video, sending and receiving faxes, and downloading email messages with attachments. With the introduction of 3G technology, smartphones were developed. With these devices, the newer technologies were overlaid with 2G to support multiple access modes, 2G, 3G and 4G. Although the 2G technologies will be phased out over time and replaced by newer technologies, the current wireless communication networks continue to utilize 2G for voice and text. That's how you can still send a text with hardly any signal, because it's using the 2G. All 3G systems utilize CDMA and WCDMA technology and fall into two groups, complying with the third generation partnership project, 3GPP, or 3GGP2 family of standards. Universal Mobile Telecommunications Service, UMTS, Wideband Code Division Multiple Access, WCDMA, and Time Division Synchronous Code Division Multiple Access, which is TD-SCDMA, are 3-generation partnership project variants. CDMA 2000, which is based on 2G CDMA1, is 3GPP2. That's confusing, isn't it? 4G systems use orthogonal frequency division multiplexing. That's going to be important later on. Within the UTRAS, LTE Advanced, or Worldwide Interoperability for Microwave Access, WiMAX standards. There we go. That's what WiMAX is. Worldwide Interoperability for Microwave Access. Oh, sounds so friendly. Okay. Just going to read a little bit more. Modulation schemes, GSM and CDMA. The Global System for Mobile Communications, originally Group Special Mobile, GSM, was developed to establish a digital standard for compatibility throughout Europe. GSM is a circuit switch system that uses both FDMA and TDMA technologies. The frequency division mechanism divides the GSM band into 200 kHz wide channels. The time division mechanism enables up to 8 different time slots or voice channels per frequency channel, wherein a single cell phone transmits in only 1 out of 8 available time slots during a voice communication. This introduces a pulsed signal shape with a pulse repetition rate of 217 Hz. Such a TDMA frame has a length of 4.6 milliseconds, and 26 TDMA frames make up a multi-frame with a 120 millisecond duration. During a multi-frame, a mobile phone transmits in 25 out of 26 possible time slots. This TDMA frame structure causes significant low-frequency amplitude modulation components to be superimposed on the RF carrier at 8.3 and 217 Hz. Furthermore, as a direct consequence of the TDMA, the peak power and the instantaneous SARs are 8.3 times higher than the average power and SAR. Note that the average power is the metric of importance for SAR determination within the context of the current safety standards. That's quite important there, actually. As a direct consequence, just highlight that for you as we read it, of the TDMA, the peak power and instantaneous SARs are 8.3 times higher than the average power and SAR. But note that the average power is the metric of importance for SAR determination within the context of the current safety standards. So this is talking, I think it's talking about when you don't have signal, it's going to really peak up there. So I'm just going to highlight all this because I think it's very good information, and it's also explaining all those letters, the acronyms. And there's a picture, a GSM frame showing peak and average transmit powers. So the way it peaks is every 4.62 milliseconds, and that's how you get pulsing. And then the average power there, and that's how they determine the SAR value. So the peak power just pulls that up a little bit. Okay, with GSM, the duplexing between uplink when the handset transmits to the base station and downlink when the base station transmits to the handset, so we're learning all the jargon here, is implemented in the frequency and time domain. Constant frequency spacing is maintained between up and downlink frequencies. In the United States, the uplink is 1850 to 1910 MHz, and the downlink 1930 to 1990 MHz. The uplink and downlink frequencies are chosen according to the cell area that is covered by a base station into which that mobile is registered. In order to minimize interference between neighboring cells, a frequency reuse policy is applied. In this approach, when a mobile phone moves from one cell into an adjacent cell, frequencies used for data uplink and downlink change in association with this movement, i.e., transmission frequencies change at handover from one cell to another. CDMA technology uses a form of coded transmission known as direct sequence spread transmission, DSSS, in which data are multiplied by a much faster pseudo-random code before being modulated onto the carrier. The effect of the multiplication is to spread the message across the whole frequency bands available for use at a given time in a given cell, but with very specific characteristics. CDMA signal access technology is based on one code division separation of mobile stations as well as base stations. This implies differences of the signal structure compared to GSM. For example, in IS-95, in the forward link downlink, a set of 64 Walsh codes, which are deterministic and orthogonal, are applied to spread and separate the individual channels in the downlink of a cell. After the orthogonal spreading, a short 16-bit pseudo-noise code is applied to further spread the signal and identify the cell. Hence, a separation of neighboring cells in the frequency domain is no longer necessary, and there is no need for for the mobile station to change its transmission frequency during the transition from one cell into another. As with GSM systems, the duplexing between the forward and reverse links is implemented in the frequency domain. In CDMA systems, an efficient power control is crucial, because all mobile stations transmit and interfere in the same frequency channel. Each mobile device decreases the signal-to-noise ratio of all the other mobile devices. Hence, the output power of a mobile phone should be kept at a minimum that guarantees good transmission quality. IS-95, also known as CDMA-1, was developed by Qualcomm, San Diego, as the first 2G CDMA-based digital cellular technology. The term IS-95 generally applies to a protocol revision, P_REV equals 1. That was adopted as a standard, TIA-EIA-95, by the Telecommunications Industry Association, TIA, in 1995. It's like 1,000 acronyms here. Over time, subsequent iterations of the IS-95 protocol, such as IS-95A, TSB-74, and IS-95B, were developed, each with incremental improvements over the previous protocols. Later, more advanced versions of the CDMA technology have evolved to include IS-2000, which incorporated much higher transfer rates than the previous 2G versions. For a further explanation of these technologies and how the NTP exposure system was designed to reproduce similar GSM and CDMA cell phone RFR exposures, please see the video presentation, Day 1 at 54 minutes, by Dr. Miles Capstick. So again, I'm going to highlight all of that. That's all very good technical information. It tells you how phones work. So the next section is sources, use, and human exposure. The predominant source of exposure to RFR for the majority of the population is through use of telecommunications and mobile internet access applications for wireless devices, and the highest human exposure to cell phone RFR occurs through the use of cellular phone handsets and other wireless devices such as tablets and laptop computers held in close proximity to the human body. Aside from telecommunications, there are other man-made applications of RFR, which include microwave ovens, radar, industrial heating and sealing, medical diagnostics, magnetic resonance imaging, MRI, and therapy, surgical diathermy and ablation, and remote tracking or detection of objects, anti-theft, radio frequency identification, RFID. There are also natural sources of RFR such as atmospheric electrical discharges, lightning, and solar and cosmic radiation. RFR exposures from natural sources are much smaller and tend to be spread over a wider range of frequencies compared to exposures to fields from man-made radiation sources. I always think, why do we learn this at school? This is much more relevant information. The use of cell phones has become widespread over the last 2 decades, and concern has been expressed regarding the potential health risks associated with use specifically by children. According to a Pew Research poll, that's PEW, approximately 95% of adult Americans own a cell phone. As of December 2015, the number of active wireless subscriber connections was 377.9 million, which exceeded the population of the United States. According to the same survey, 49.3% of households in the United States utilize only a wireless phone and not a landline. There has been a great deal of focus on the possibility of increased risk of brain cancer because of the traditional use of these devices in close proximity 0 to 2 centimeters to the head. In general, apart from the case when very close to the antenna, the level of RFR exposure from a cell phone is inversely proportional to the square of the distance of the body from the device's antenna, resulting in the highest SAR levels in the parts of the body nearest to the antenna. So that's the inverse square law, isn't it? As you get so far away, the radiation diminishes. Accurate and detailed measurements of RFR exposure in humans are difficult to estimate because the output power of wireless devices constantly varies, depending on several factors. Overall, the network carrier adjusts the output power of each connected device to the lowest level overall that is still compatible with a good quality signal. This adaptive power control occurs continuously and is achieved by logarithmic downscaling of the time average power from the maximum of 0.125 or 0.25 watts to a low level as low as 1 milliwatt. When in use, the output power and subsequent exposure to cell phone RFR from the device is increased compared to that in standby mode. Therefore, exposures are related to the amount of active time a user spends on the device. I'll just jump in there and say that I've measured phones giving out some serious stick when I've got the meter next to them and they're on standby mode. So the newer phones, they're much busier. They're not like the older phones in the 2G, 3G era. The output power of a device changes based on the signal received at the base station. Decreases in signal strength result in higher output powers. Therefore, there are increases in the output power as the distance between the device and the base station increases. If there are physical obstacles between the device and the base station, reflections off buildings or other structures, and during handovers from one cell to another, in the case of GSM. The proximity of the device to the body and the type, number and position of antennas in the device are other important factors affecting the amount of exposure to RFR. Potential exposure to RFR used in cell phones also occurs from the cell phone towers that form the network. While modern towers emit substantially more power than devices, exposures from base station antennas are considerably lower to users than from the handheld device. Typically, base station antennas are placed at heights of 50 to 200 feet in order to adequately cover a cell. The antennas direct RF energy towards the horizon with some downward tilt. As with all forms of radiation, ionizing and non-ionizing, the RF energy level decreases rapidly as the distance from the antenna increases. As a result, the level of exposure to RFR at ground level is very low compared to the level close to the antenna. Well, now they're putting antennas right outside your bedroom windows and right outside your house. I have pictures on my phone of huge cell towers, that must be 100 feet high, and they're right outside people's houses. So how can you do that knowing this? So I'm just going to highlight that again. Some base station antennas are installed on rooftops and at the top of lamp poles that are in close proximity or adjacent to office space and residential buildings. Occupational exposure can occur during maintenance of base stations. As a result, the FCC established guidelines for occupational exposures. Safety guidelines and regulatory compliance are discussed below. The levels of RFR inside buildings with base station antennas mounted on the roof or on the side of the building are typically much lower than the level outside, depending on the construction materials of the building. Wood or cement block reduces the exposure to RFR by a factor of about 10. Due to the directional nature of the signals, the energy level behind an antenna is orders of magnitude lower than in front of the antenna.